Hello and welcome to our presentation for our senior design project. Our project was the COVID decontamination chamber. Here's the team. You have me, Dane, Riha.
I'm Jacob Talaga.
And we are from the Department of Mechanical Engineering and Technology. Our advisor for this project was one of the professors in the MET department, Scott Wagner, and our sponsor was MTU I-Corp and Scott Wagner himself. The purpose of our project. The main purpose of this product is to decontaminate tools or PPE used by medical healthcare professionals in everyday use. With the extensiveness of the past pandemics and the current one we're currently experiencing, we were tasked with making our product user-friendly and repeatable on a large scale to help fight the spread of disease everywhere. We want our product to be able to be brought to schools, hospitals, any public government building where they do testing on a large scale. So like with COVID testing, when you used to get your COVID test and everything, they would have medical professionals and they would be completely covered in scrubs, gloves, glasses, masks, anything that they can use to help prevent the spread of disease through them and spreading it to the multiple people getting tested. So our product would be, you take all that PPE and those tools, and you would put it into our project, and with a couple touches of a button, it would decontaminate it. Our idea was to have schools and hospitals and government agencies be able to have access to these. We wanted to make sure that our product is 100% reliable, so we added as many forms of decontamination that work together as possible. We had a fair amount of ideas, but the ones that ended up making the cut, we'll talk about later into the presentation. The requirements for the chamber. Design and build a working decontamination chamber for tools used by medical professionals. Limit the modes of virus or disease transfer from operator to operator while they're using it. So this includes if it's just one person using tools and putting them in there and then cleaning them, we don't want the spread from the tools to the operator, or if an operator touches a handle, or if an operator uses the touch screen, spreading any disease that could be on themselves to another operator. We wanted to run the whole entire system from an external touchscreen. This makes it really easy because the interface just pops up and you can put in different specifications, like you can do different times, moisture levels, how long the spray valves coat and cover the whole entire interior, the temperature, duration, stuff like that. So we wanted that all to be run from a user touchscreen, very self-explanatory. So when you do take this product and you give it to someone who has maybe never used it, it's very intuitive and self-explanatory. And then lastly, we had to add different modes of decontamination. We already had two that was done by the previous group, but we added one of our own. So that brings us to our starting point. The model of our fridge is a master built MBR 49S refrigeration system. This was donated to us by one of our sponsors. They didn't sponsor the project directly, but they had the fridge and they let us use it. They also donated a couple of the other smaller things, different sealing materials to make sure that there's no leaking and stuff like that. So we had to take this fridge, and if we were to mass produce this, I don't think we'd start out with a fridge. I think we would design the chamber of our own and then build off of that. But for our prototype, our model used a refrigeration system that we were able to access. The parts that were already assembled. So our project is a continuation of a senior design project that happened last year. That group, they were never able to finish it or put on the finishing touches of it. So we had to pick up their project and start from there. The things that they had already assembled, the spray valves, so all the piping and all the valves, so that when you have disinfectant spray coating and covering all your tools and PPE, they did a lot of research on seeing what kind of valves have the best surface area coverage, stuff like that. They mounted the heating element and did a little bit of the wiring and connecting it so it could be connected to the Raspberry Pi. They did have a drainage system. We'll talk a little bit more about that later. And they did some of the wiring for the Raspberry Pi. What we needed to finish, install an operating system to the Raspberry Pi and the control systems. When we got the project, the Raspberry Pi was already there with the touchscreen and everything, but we went to go turn it on, wouldn't turn on. So we had to troubleshoot a lot of the problems that way. We did have to redesign the drainage system. We didn't think it met our level of satisfaction, so we did a simplistic design for that. Add another form or forms of decontamination. We had a lot of good ideas, but we did have to settle on one that would work with our system and incorporate and work together. Add safety elements to protect the operator. Just small little things to help stop the spread of disease. First off is the computer diagnostics. As MET students that have never used control systems, this was a learning curve for us. We have very little to no experience dealing with Raspberry Pis, dealing with wiring, and dealing with touch screens and all that. So we had help from one of my fraternity brothers. He came in, kind of showed us the ropes, helped us guide us through the whole process of doing the wiring to downloading software to the Raspberry Pi, hooking up the SD card, letting us know what tools that we needed that we didn't have on hand that we ended up having to order. So we wanted to say thank you to him. We do acknowledge him later on in the presentation, but thank you so much for helping us out with that one. At first look, the Raspberry Pi did not seem to turn on or activate the touchscreen. With further investigation, we learned that the Pi had some parts that were broken and all the code from the previous designers was corrupt. So we had a general idea of what their code was and looking at through what was downloaded on the Raspberry Pi. And we did have the SD card, but the code wasn't running. The code didn't work. It was corrupt. So we had to restart all of that. Code in the Raspberry Pi. We had to download a new operating system onto the SD card. Make sure that lined up with the Raspberry Pi that was already purchased. We had to rewrite the corrupt code and write new code for the additional systems. Troubleshoot all wiring to make sure each system was working. We had a ton of wires, as you can see on the picture on the right. That's just some of them. Each control system that we had that ran to the Raspberry Pi had to be wired specifically in a specific manner, and we had a lot of wires being run. They have housing for the wires on the right side. That's in the picture, that's the black little strips. Those housing is all the wires for our project. We had to get a new power supply for the whole entire system. As we added more elements, the power supply wasn't big enough, so we had to purchase a new one. We also had to design the user interface. So as you can see on the screen on the right, a user interface would pop up with different just buttons that you can press, different inputs, and you can set those to any specifications that you would need. There are minimum requirements for different, we'll talk about a little bit later, but for like duration, for how much needs to be sprayed, what chemicals and stuff like that. But if you did want to change it to make sure that your tools are being disinfected properly, you were able to set your own specifications. The heating system and spray valves. We didn't change anything with the pre-existing system, but we did check to make sure that the settings on the heater were effective and the chemical used was strong enough and the proper disinfectant. The disinfectant used, we ended up changing this from the previous group. They chose a specific type of decontamination spray, but we changed it to isopropyl alcohol. We're going to do 70% isopropyl alcohol with 30% water. The reason why we chose this is isopropyl alcohol is very commonly used and one of the best disinfectants that you can get in the market that is readily available. You can get it at any store. The reason why we chose 70% though was because we wanted to make sure that we could maximize how much we're cleaning without also preventing the isopropyl alcohol from either evaporating due to the heat, which can get toxic, which couldn't be good for the operators. So if you do 30% water, it keeps it saturated, keeps it into a liquid form, preventing the operator from getting sick or inhaling this. Also, with 30% is you can spray this onto a lot of different tools and PPE and they won't melt. They won't deteriorate, corrode, or anything like that. And this keeps the inside of our system safe and the tools that you put inside. With COVID-19 specifically, it was discovered that the inside of the decontamination chamber would need to maintain a temperature of 7 degrees Celsius for 5 minutes to kill the virus. We actually upped these numbers a little bit, raised these numbers, just to make sure that the safety was followed and make sure that everything was properly disinfected. The drainage system. The old drainage system that was put into place was neither sturdy nor effective. It was made from PVC and silicone, and it was very loosely. When Jacob and I first got the project, we kind of were messing around with it, pushing on it, seeing how sturdy it was, and it was breaking beneath our fingertips. So we ripped out the whole thing, started from scratch. We did reuse some of the PVC to actually build the mount, or the mount, the cover for the Raspberry Pi. So we were reusing and repurposing that material. So for our design for it, we kept it really simple, and we just removed the whole entire thing. And with fridges, with condensation that builds up on the inside, it naturally cools towards the center. So we put a hole there and then two on either side, so that if there's a fair amount, if the spray valves are really going and it's saturating them, it can just drain more effectively and more properly. The only thing that is a little bit iffy with our design that the operator might have to do is, if for some reason it dents or curves or warps with heat, you might have to take like a squeegee and kind of squeegee the water into the holes, which you would have to do anyway to make sure that the sides of the walls actually get cleaned properly after you use the machine. So it wouldn't be that much more to actually squeegee it into those holes.
So going more into depth into some of the additional safety elements we added a foot handle to the bottom of the main two doors. We added UV lights throughout the interior. Obviously the housing that Dane had mentioned with the extra PVC to cover the touchscreen, and then just some interior lights, LEDs, just to help out. So starting with the foot handle, the whole idea behind the foot handle is you have an operator carrying a tray of supplies, whether it be gloves or masks or visors, whatever it may be. It's a full tray, and they obviously can't waste a hand and reach and open the door. So the idea behind this is to simply let them use their foot and pull the door open. Also, a side effect of this is there's less touching involved. Obviously, without having to use their hand to pull the door open, they limit the spread of any kind of bacteria that may be on their hands. So it was a simple design, just a metal 3x6 plate that we bolted near the center of the entire fridge on both doors. Yeah. So moving on to the UVC germicidal lights that Dane had mentioned as one of our main additions. From what we could find, there isn't a whole lot of medical research for COVID specifically on how UVC lights react and how effective they truly are. Especially when it comes to exact temperatures, durations, and wavelengths for lights. We found one study, I believe it was out of Purdue, that actually gave us the temperatures and durations that sufficiently killed the virus. I believe they're listed further on in this presentation. We only added one light just because to keep it within budget and keep it reasonable. So we added it central to the fridge, and it gives direct contact to most of the contents. UVC, we wanted to mention also that UVC lights are relatively safe to use as long as the doors are completely shut and the room is ventilated, because they can create some ozone. And this is just expanding on some of the safety and health hazards that come with using UVC lights. The operator should not have direct contact with light exposure. It can cause burning to your eyes and skin, as well as damage to the eyes if it's directly exposed. Some UVC lights can create ozone in confined areas, and they can, especially if the bulb is to break, if it's dropped. Another thing is some of the lights contain mercury, and that can cause a lot of issues. And the exposure to mercury can just be caused by bumping or touching the light or breaking the light. Thankfully, the light we implemented does not contain mercury. So for proper usage, just to keep these safety factors in play, the door must be fully shut for the duration of the decontamination process. And we want to have sufficient ventilation in the room of the chamber if any ozone is to be created during the process. We also added some LED lights, simply just to allow the operator to safely obtain any materials. If there's knives or whatever have you on the tray that they're trying to reach and they can't necessarily see what they're working with, obviously that can be a bad situation. So we wanted to ensure that there was proper lighting throughout the entire interior of the chamber. So we added 4 LED strips to the back wall to allow that there is sufficient lighting inside. Moving on to the housing for the touchscreen, as Dane had mentioned earlier, we kind of just took the old PVC from the drainage system and repurposed it to create this. With all the electronics mounted to the sides of the chamber, we needed something to cover it up to prevent it from water damage or from being bumped or being tampered with. And the main panel is just attached using magnets, so it's easy to service, but at the same time, you really can only access the internals if you plan to actually perform maintenance on the system. So wrapping this up, we believe our product is a good basis for what should be included in a decontamination chamber, and having this many different modes of decontamination. We hope our idea can help with the next global pandemic or everyday use in hospitals. We also listed some of our future improvements that we think would help with the product. So this product was kind of built on the idea that you have an old existing fridge and you can kind of use this kit to kind of transfer it or translate it into a decontamination chamber. But in all reality, the entire chamber could be repurposed to be solely working as a decontamination chamber. Some of the other improvements we thought of was just using better products for sealing and fasteners. We were kind of on a budget to keep within, so we had to use less than ideal materials at times. Another thing would be better wiring organization and electronics placement for the operating system. Obviously on the side, there is like a chance to get bumped and there's a chance for tampering. So moving that to a different location would protect that. Overall, using a different container that is lighter, cheaper, and easier to work with. The fridge is made of very strong stainless sheet metal. It was trying to drill and tap into it was less than ideal, and a lot of it was there was a lot of headache created from trying to work with the fridge. Another thing would be adding integrated systems instead of attaching a new system to the interior walls. So obviously, if this were to be a product from the get-go, there wouldn't be all these loose parts, or not necessarily loose parts, but third-party parts within. They would all be kind of created, pushed together. The last thing was, like we had mentioned, relocating the control panel, ideally into the wall of the chamber, just to kind of keep it all contained. This would just ensure that all components are hidden, as well as preventing the electronics from being tampered with. We'd like to make some acknowledgements. The fridge we had originally gotten from Healthy Ridge Farm LLC, and we would like to thank them for the donation. We'd like to thank Kyle Ott for all the help with the code throughout, as well as our advisor, Scott Wagner. And these are a list of our sources, and thank you for your time.